Hello, my name is Alexander Naumenko, and today I'm going to talk about insights about prime numbers and the Goldbach conjecture. And I would like to start with this quote by Underwood Dudley. Uh, Indeed, when we talk about prime numbers, it really seems that there is some order or pattern about them, just a little bit below the surface, just a little out of reach. And now let's talk about the Goldbach conjecture. Here you see a little piece from the Wikipedia, and it says that it was introduced in around 1742, and still it is not proven. And about the same time, famous mathematician Euler stated that he regards this conjecture as a completely certain theorem, although he cannot prove it. So what the Goldbach conjecture is about? It states that every even number greater than 4 can be represented as a sum of two prime numbers. For example, 30 has three such representations, decompositions. 7 plus 23, 11 plus 19, 13 plus 17. And another even number, 98, has the smallest prime number in its decompositions, 19. We will talk about it more later. When I will talk about my approach to considering the Goldbach conjecture, I will use modular arithmetic a lot. Here is a piece of text from, again, Wikipedia, and the modular arithmetic is, in essence, all about wrap around some number, which is called modulus. And it was introduced by Carl Gauss in 1801, so it's a pretty old technique. And now I would like to talk a little bit about observations that I encountered in my research. When we multiply numbers from the same sequence, like 5 plus 6t and 5 plus 6q, we will end up with the number from the different sequence, 7 plus 6s. And when we multiply 7 plus 6t by 7 plus 6q, again we will come up with the number 7 plus 6s. And only when we multiply different numbers, 5 plus 6t by 7 plus 6q, we will have a number 5 plus 6s. So if we try to find some average number for the first consecutive odd primes as percentage of the biggest one of them, we will come up with this interesting number 0.463. So I checked that for the first 10,000, and in fact there were 1,227 primes, and that number that average number was received based on that sample. But it really looks like we have something here. So can we infer more from it? From this simple derivation, we can come up with a formula for next prime number based on the value of current prime number and the number of primes up to that current prime number. So this formula is pretty good, but if we try to come up with a more general formula which doesn't depend on current prime number, it quickly becomes very inaccurate. Now probably it's time for a little joke. Let's switch to a more involved version of a proof. So being a programmer by trade, I wrote a little program to calculate for any first consecutive odd primes, the smallest even number which produced only composite numbers when any of those primes was subtracted from that even number. And the next table shows the result produced by that program, and we can see that the function is stepwise because some values repeat, but from the other look at this table, we see that the number grows very fast because this functional dependency is difficult to understand and of course to prove. I abandoned this approach and switched to the proof by contradiction. So what requirements for a proof we may have for the Goldbach conjecture? Just like Euclid did in his proof of the infinitude of primes, we should be ready to come up with some general proof which doesn't rely on any specific prime numbers or any specific relationships between them. So with that, we really start with the latest approach I took to the proof of the Goldbach conjecture. And it is a proof by contradiction. So we assume that if Goldbach conjecture is wrong, then for some even number 2n, and for each prime number pi below n, we have 2n minus pi is equal to some product of primes below square root of 2n minus 3, which I call basis primes, and some number m, which may be composite or prime. It really doesn't matter. So really considering this relationship between primes, I was really, it was difficult for me to somehow relate those primes pj and py. Why? Because first of all, I wanted to operate using as few parameters, different parameters as possible. So And it took me a while to come up with the following idea. So the above relationship is true for prime numbers congruent to 2n, our even number, modulo basis primes. Uh, so here we see how we use the modulo arithmetic. And the next table will illustrate that idea further. So we have this number 2n, in this case 32, which is power of 2, so it is not divisible by any prime number. Uh, why it's important, I will talk a little bit later, but first let's analyze this table. So here we have modulos of 2n divided by 3 and 5. And its modulos are the same, namely 2. And we see here below the pairs of Goldbach decompositions for 32. And they do not include 5 and 7. Why? Because 5 produces 2 modulo 3, and 7 produces 2 divided by 5. 11 produces 2 divided by 3 again. So we will not see those primes in Goldbach decompositions. But 13 and 3 do not produce 2 divided by 3 or 5. Therefore, they are present in the Goldbach decompositions. Let's talk about what we can say about divisibility by some prime and Goldbach decompositions. If we have even number, for instance 30, and we consider that it is divided by 3 and 5, so we will have modulus here, residues here, zeros, but we see that any prime divided by any other prime that never produces zeros. So if even number is divisible by any of its basis primes, then that basis prime will not participate in sifting out these primes between n and 3. So if we want to find the numbers that are that have fewer decompositions, then we should pay attention to powers of 2 or to numbers of the form 2 times some bigger prime. Definitely that that even number will have some Goldbach decomposition, namely that prime plus prime, it will give us 2 times that prime, but other primes may be pretty severely sifted out using this idea. So but still that will not produce prime that even number that has no Goldbach decompositions. So when we are talking about possible candidates for even numbers that have no Goldbach decompositions, then we should probably pay most attention to powers of 2. But let's move on and consider other parts of our proof, because really, in order to prove the Goldbach conjecture, we have to prove that there are primes below n that are not congruent to 2n modulo any of the basis primes. In fact, we can formulate several statements similar to this one, and in my proof I decided to go with a slightly different statement. So first, let's consider an estimate for n. We will take the biggest basis prime, we will have its square, and then we will add 3 to it and divide that by 2. So it will be a pretty good lower bound for our number n. Because in fact, you should understand that the same set of basis primes serves its purpose for quite a range of even numbers. Because, for instance, we may consider even numbers from 54 to 104. So the range is above 50. And still, we will have only 3 basis primes, namely 3, 5, and 7 for all those even numbers. And if we consider 7 squared plus 3 divided by 2, we will have 26. So all the prime numbers below 26, we should consider those prime numbers, and we should prove that for any possible residue system over those basis primes, we will still have some prime number among those prime numbers below 25 that is not congruent to that residue, to any of those residues modulo given prime number. So how can we prove it? Let's move to the next slide, and we will consider what we want to prove. And we will prove that for any first consecutive odd primes, with the last one being P maximum, we taking any residue system over those basis primes into account, we want to prove that there will be a prime number below that estimate of n that is not congruent to those residues modulo those primes. And to prove that, we will use a two-stage so-called Goldbach sieve for odd numbers. The first stage will be a famous sieve of Eratosthenes, and the second stage will be removing all primes congruent to a given residue of a given basis prime. And to prove that, we need to consider those two possible groups of odd numbers. The first group I call odd numbers covered by given basis primes that we already considered. And what I mean by odd number being covered by some basis prime. First of all, if this odd number is a multiple of that basis prime, it is considered to be covered. But also, uh, if that odd number divided by that basis prime produces a given residue, then I also consider that odd number to be covered. So, and all the other odd numbers will be in the remaining group, in the second group. And if we consider that the first stage of our sieve is essentially the sieve of Eratosthenes, then the remaining group, after taking into account all the basis primes, it will contain only prime numbers. And taking into account the second stage of our sieve, mainly sieving out prime numbers that are covered because they produce the needed residue divided by basis primes, then we uh, we are left only with those prime numbers that satisfy what we want to find, namely primes that are not congruent to any even number modulo our basis primes. So let's proceed to this slide. And here we want to introduce a very simple idea, in fact. And in order to understand this idea, we only need to understand that prime numbers are independent of each other, meaning that when we divide prime numbers or try to find the greatest common divisor of prime numbers, we will end up with 1. And so when we consider consecutive odd numbers, then we do not have any dependencies between different groups of odd numbers. So we already talked about two groups in our discussion, and essentially for instance, if we consider several of the basis primes and we sieve out odd numbers based on those basis primes, and we take the next basis prime to apply sieve with the relation to that basis prime, then we will have this independence in play, because the group that contains already covered odd numbers and the group that contains remaining odd numbers will have the same share of numbers covered by a new basis prime. And that's very important for our approach that we are taking in this proof. So let's consider this slide, and the idea stated here. So applying each basis prime p during both stages of the Goldbach sieve, we are left with the p minus 2 over p share of the primes in the in fact of the odd numbers in the uncovered group, because uh, before we apply all the basis primes to the uncovered group, we cannot say that we have only primes in that group. But after we apply the last basis prime to that uncovered group, we are left with uh, only primes in that group. So, and really we remove 1 over p share as multiples of that prime and 1 over p as congruent to a given residue, give modulo that basis prime. So, and now we again, I reiterate that we are considering odd numbers in ranges between uh, our estimate of n for consecutive primes. For instance, given prime numbers 5 and 7, we consider a range between 5 squared, which is 25, plus 3, it's 28. So we consider odd numbers from 14 to 26, which is 7 squared, 49, plus 3, 52, divided by 2, 26. So odd numbers from 14 to 26 should be covered somehow by all the basis primes below 7. So essentially we are talking about 3 and 5. So let's proceed to our proof. And for the main step of our proof, we will use mathematical induction. And as the first step of that induction, we consider that our basis primes contain only one element, which is number 3, and therefore we consider odd numbers below 14, which is next prime number squared plus 3, and that sum divided by 2. We have 6 odd numbers there. We do not count 1 for known reasons. And given that we apply 3 to these 6 odd numbers, we are left with 6 times 1/3 gives us 2. So we are guaranteed that we will have at least 2 uncovered primes, no matter what residue system we have over that prime number 3. So since we have uncovered primes at the first step, we can proceed to the next step of our mathematical induction. And here we just assume that for some set of basis primes ending with some prime number p, we have some positive number of odd numbers after this two-stage sieve. Therefore, we have those uncovered primes. So we may assume that at this stage of our proof, we still have some uncovered primes. So our Goldbach conjecture still holds for this number. And now we switch to the next step in our proof. And here we want to prove that the set of basis primes, including the next prime number, will also have some uncovered primes below our estimate for n, given by the formula above. So we need to consider how we increase the number of odd numbers considered for this sieve, and the number of odd numbers grows by this growth factor that you see on the screen. So what I mean by 2k, we know that prime numbers except for 2 are only odd numbers. So next prime number after some prime number p will be different from number p by some number 2k. If in case of k being equal to 1, we will have a twin prime. But if k is bigger than 1, we will have some difference bigger than 2 between consecutive primes. So in fact, we do not know what the next prime is, but we sure know that there will be next prime, because Euclid already proved that there are infinitely many prime numbers. So we can just know that we will have this ratio between our estimates of n, and as the next component to the difference is this ratio. Essentially, here we have the same ratio as we discussed earlier, namely prime number minus 2 divided by that prime number. So we know that the total number of odd numbers below n that we need to consider has increased when we added new prime number to the basis primes. But on the other hand, we have this ratio applied to this increased number. So before on this step, before we also produced these multiplications. So we first increased the number of odd numbers, but then we decreased that number by this ratio for that prime that was included on the previous step. But now we should consider whether we multiplied a previous number of remaining odd numbers, which are essentially prime numbers, and if we multiply them by these two ratios, whether we will still be in the positive area, meaning that the number of remaining primes that are not congruent to some residue systems over basis primes is still has still some numbers in it. So what do we need to prove at this stage? to finally prove what we wanted to prove here. Essentially, we need to prove the following. If we prove that product of those two ratios is bigger than 1, it will not only prove the final piece needed to prove the Goldbach conjecture, but it will also explain why the number of Goldbach decomposition grows with n. And here we have very simple derivation. First, we see here product of these two ratios. And we see that we can cancel out these two components, leaving only one here above. So here we have somewhat clear picture. And already here on the second step of our derivation, we can clearly see that the number above is definitely greater than the number below. Because here we see a number which is bigger than p, and here we see a number which is at least p. In case of twin primes, we will have here exactly p, but here we will have p plus 2. So if k is greater than 1, we will have even bigger number above, which means that the total ratio is definitely bigger than 1 for any k equal or bigger than 1. And we know from the previous steps that k should be bigger or equal to 1. So this step finalizes our proof. Therefore, because we know that the same set of basis primes is valid for quite a range of even numbers, and those even numbers divided by all those basis primes produce different sets of residues. So in our proof, we relied we didn't rely on very specific number, even number, or any specific residue system over basis primes. We allowed for any set of residues. Therefore, our proof really considers all the general cases of that are possible in this case. However, I want to stress that in fact we do not have all the possible combinations of residues for any given even number. And I will state my conjecture a little later. First, I want to reiterate what we proved in this video. So we started our proof by contradiction with an assumption that for some even number 2n, all the primes below n are congruent to 2n modulo sum of its basis primes. So we showed then that it is impossible because the number of basis primes is just too small to cover all the primes below n. Therefore, the Goldbach conjecture is indeed a certain theorem, as stated earlier some time ago. And now I want to state my conjecture with relation to the Goldbach conjecture. Uh, Essentially, I analyzed uh, Goldbach decompositions for numbers up to 10,000, and it looks like at least one of the primes in Goldbach decompositions will be below 3 times the biggest basis prime for the considered even number. Uh, why we have this conjecture? Because first of all, I want to reiterate that we do not have all the possible combinations of residues over basis primes uh, given any even number. Why is that? Because in order to have all the possible combinations, we need to have even number which is equal to two, actually, which is equal to primorial of those basis primes. But it is definitely bigger than any even number, uh, considering the relationship between even number and its basis primes. So what I think, there is some relationship between those residues that do not allow uh, the smallest prime in Goldbach decompositions to be above this expression that is stated here. But again, I do not have any clear way to prove this conjecture. That's why I leave it as is. And with that, I just want to say this final piece, that definitely this is not a rigorous proof, but it really looks like we have all the reasons to believe that the Goldbach conjecture is valid and indeed a certain theorem. Thank you for your attention. See you later.